To start the demonstration, pull down File, Open, double-click on the folder name, select the file project.apex, and then click Open. Here, you can see the 4 different pre-built subassemblies for each concept. The first subassembly is the tension case, where we apply negative 5,000 Pascal pressure on the face of the tool block glued to the square bar we are analyzing. With the bar face being 0.016 meters squared in area, this translates to a 50 Newton force pulling the face of the bar. The second subassembly is the compression case, where we apply a positive 5,000 Pascal pressure to the same face as in the tension case. This translates to a 50 Newton force that pushes the face of the bar. The third subassembly is the bending case. Here, we've applied 2 1 Newton forces in opposite directions on our tool to simulate a bending on the bar. With the length of the moment arm at 0.10909 meters, this translates to a bending moment of 0.218 Newton meters acting on the bar. The fourth and final subassembly is a combined case where we've applied 2 45-degree angled forces to our tool. This is to simulate a bending due moment of 0.154 Newton meters and a bending due to force of 1.414 newtons. Notice that the model consists of 3 parts glued together: the bar, the base on which the constraints are applied, and the tool on which the load is applied. The model is ready to analyze, so let's run it. Right-click Assembly 1 in the model tree and select Set Analysis Context. When Apex reports that there are no offenses identified and that the current analysis context is ready for submission to the solver, you can proceed to run the analysis by clicking the yellow running man. Now that the analysis has completed, let's first take a look at the tension case. Click on the Post tab and double-click on Static Scenario Assembly 1. In the Model subsection, we hover over the visibility icon on Assembly and select the empty box to hide all the parts in the subassembly. Next, we hover over the tension bar and click on the check. Fit the part into the screen by pressing the right and left mouse buttons simultaneously. Here, we see the deformed shape of the bar in tension. In this case, the deformed shape is exaggerated. We can change the scale by changing the deform scaling option. Let's try true scale. Now let's show the fringe plot by clicking the fringe icon. If we hover the cursor over the spectrum, we see that we are viewing von Mises stress. Let's change it to X component. We see that the stress value is between 28.9 and 37.1 kilopascals, which correlates to our closed form solution of 31.25 kilopascals. We can also change the result quantity to show displacements translational, which also matches our closed form solution value of 1.3 times 10 to the negative 7 meters. Now let's look at the compression case. Hover over the visibility icon on tension bar and select the empty box to hide it. Then hover over the compression bar and click on the check. Fit the part into the screen by pressing the right and left mouse buttons simultaneously. Here, we see the deformed shape of the bar in compression. Change the fringe plot to show stress again by hovering over the spectrum and changing the quantity to stress. We see that the maximum stress falls between 28.9 and negative 37.1 kilopascals, which correlates to our closed form solution of negative 31.25 kilopascals. If we change the result quantity to show displacements translational, this also matches our closed form solution value of negative 1.3 times 10 to the negative 7 meters. Now we will repeat the same steps to show the results of the other 2 cases. Hover over the visibility icon on the compression bar and select the empty box to hide it. Then, hover over the bending bar and click on the check. Fit the part into the screen by pressing the right and left mouse buttons simultaneously. Let's turn back on relative scaling in the deform scaling options. Here, we see the deformed shape of the bar in bending. Let's show the fringe plot of the X component of stress again. Here, we see that the top is in compression with a negative value of negative 21 kilopascals, and the bottom is in tension with a positive value of 21 kilopascals, which matches our hand calculations. If we change the result quantity to show displacements translational and then select Z component, it also matches our closed form solution value of 6.7 times 10 to the negative 7 meters deflection of the tip end. Finally, let's look at the combined case. Hover over the visibility icon on bending bar and select the empty box to hide it. Then, hover over the combined bar and click on the check. Fit the part into the screen by pressing the right and left mouse buttons simultaneously. Let's turn back on true scaling in the deform scaling options. Here, we see the deformed shape of the bar for the combined case load. If we hover over the area of the spectrum, we see that we are viewing x component of stress of approximately 59,800 pascals. This is slightly different from our hand calculations because in our closed form solution, we assume the forces are applied in such a way that they are perfectly aligned with the centroid of the beam. However, in the real part, due to the thickness of the tool, the forces aren't squarely aligned with the centroid. Our calculations do not account for this, and thus causes the slight discrepancy between the displayed results and our closed form solutions. If we were to decrease the thickness of the paddle, we will find that we get closer and closer to the theoretical results. Now if we change the result quantity to show displacements translational, we can show the displacement in the y direction, which is the direction in which the part most deflects. This matches closer to our hand calculations of 9.86 times 10 to the negative 7 meters. This concludes this demonstration.